Okay, welcome back to another talk in the virtual seminar of Geometry with Symmetries. It's a great pleasure to introduce Sigmundur Gudmundsson, and he will talk about minimal submanifold via harmonic morphisms. Thank you, Sigmundur.
So first of all, thank you very much for running this series of seminars online and inviting me especially. I'm very proud of this. I've been following your series for some time. It's not always possible for me, but online, but at the same time, but I've looked at many of the, on YouTube, what you've been doing. You've done a great job. So my title is Minimal Submanifolds via Harmonic Morphisms. Minimal submanifolds are, of course, something absolutely central in differential geometry. Harmonic morphisms are less known, and I will now introduce a method that has sort of developed by me and my co-workers. And then just to make some propaganda, the bibliography of harmonic morphisms is a bibliography that I have been running for 40 years. And if you're interested, you could have a look at that, just Google it, and there are many things there. So this is my outline. I will try to keep this non-technical, just give you an overview of what is going on. So this is the setup. So I'll start with something really, really simple. So Jacobi, we all know him. In 1848, he had the following. So at that time, holomorphic functions on C were pretty well known, not so much studied, but harmonic functions on R3 were less known. So he had the idea of trying to compose holomorphic functions on C and then get harmonic functions on the three-dimensional space. That was the idea. Now, and he came to the conclusion, it's very easy, I will show you one line proof later on, that a map is a harmonic morphism if and only if it's harmonic and horizontally conformal. What does that mean? Well, if you write phi as, the real part is u and the imaginary part or the other part is v, then they both have to be harmonic and horizontal conformal. What does that mean? That the gradients of u and v are orthogonal and of the same length. So to prove this is almost trivial. You just take the Laplacian of the composition, and then you see if this is zero for all holomorphic function f. It means that this has to be zero, and this has to be zero here. This is the bicomplex linear scalar product. Okay. So this is the sort of first. Now, notice this, you have to think about it. This is after Weierstrass produced his Weierstrass representation of minimal surfaces. And we all know that, and you see that this reminds us very much of this. So it's the conformality that forces this to be of this type, and then the holomorphicity of f and g that is means that this is a harmonic morphism. Yeah, so he could prove that. But if you now fix Z and then solve for you see this is a real two equations. So that means that the solutions to this for a fixed Z is a fine line in R3. Okay. He tried to show that every solution to the problem could be found this way. He did not succeed. But 140 years later, two guys, first of all, they used sort of modern methods for this, but then they later found a sort of classical proof that every solution to the problem locally is a solution of this. So if you have any questions, please do not hesitate to ask. Any questions so far? No? Now, if you choose G to be this and F to be this, then we get this simple equation that every a good high school student can solve. And this is exactly what we get. So here.
Sigmund, your microphone is not in the right place.
Okay. Can you hear me better now?
Yes, thank you.
Okay, sorry about this. So you see that every high school kid who is clever can solve this, and it turns out that this is now a map from if you take a circle in the x1, x2 plane of radius r, it means that this is 0, this is real, and this is 0. It means it's in the xy plane. Then there are lines going out and filling the space, and the fibers are lines. And for later discussions, these lines are of course minimal submanifolds of the R3. Yeah, they're geodesics, of course, straight lines. This will turn up later. Any questions, Emilio?
No.
No. So now, Fuglede, a good friend of mine, he died 5 years ago, and Ishihara, a Japanese, they did not know about the paper of Jacobi. Fuglede found it later in the cellar of the Maths Institute in Copenhagen. I was a postdoc with him, and he told me this. Then we met Ishihara in a great conference in 1990. Wait a minute, 1997, I guess. And unfortunately, he could not speak English, but his wife was there and translated everything. It was great. So they completely independently defined this in the Riemannian setting. So if you have a map between Riemannian manifolds, it's called a harmonic morphism if it pulls back harmonic functions, real-valued functions, to real-valued functions on, harmonic functions on the codomain. This looks really, really analytic. And why should a geometer be interested in this? So then they showed both independently that it has to be a harmonic map, which are well known, but also horizontally conformal. What does that mean? So if you have a point in M, you take the tangent space and it splits into the kernel of d phi and the orthogonal complement. So now we're not talking at every point, but almost all points. There are points where this does not work, but the points of such a set is it's a very, very small set of, how do you call it, dimension at least two less, yeah? And then you have this, we all know what harmonic maps, they horizontally, what conformal maps is, but this now only applies to those that in the horizontal space. So this is exactly what Jacobi did in the other case. So it's the same, yeah. But now if you want to solve this or find solutions and so on, this is the harmonic map equation, which is quite well known. You see that here you have this terrible nonlinear part. This is the Christoffel symbols on M, and here on N, yeah, and here the Christoffel symbols of M. So in general, this problem here is very difficult. But we want to not only solve this, but also this one. And the horizontal conformality, which I explained earlier, means this. And here you have to check that I'm only going to concentrate on the case when n is 2, when you're going into the complex plane, because the rest is pretty overdetermined and nonlinear and very difficult. But you see that this here is nonlinear. If we are looking for the complex plane, then this H alpha beta is just delta alpha beta. So this is easy, but you still have this nonlinear problem, and this is, the difficulty lies here. If you take the complex plane, then this is just delta alpha beta. No, then this is 0, as we all know. The gamma for the flat space is 0. So in that case, which I'm going to talk about, this is linear, but this is nonlinear, and the difficulty lies here. No? Okay. Any questions so far? Emilio? So now, why am I interested in this? It turns out that if you go from a Riemannian manifold into a surface, a horizontal, you assume that this is a horizontally conformal map, then it's harmonic if and only if its fibers are minimal. This is my main reason why I'm interested in this. So if you, for example, if you pick this as the complex plane, and you have a regular image, then that is minimal. If you can find such solutions to this nonlinear problem, then you have found many minimal submanifolds of this thing here of codimension 2, because if you're assuming that it is, horizontally conformal, that means that the pre-image of any regular value is it's a two-dimensional submanifold, but it has to be minimal. And this is the main reason why I have spent 40 years of my life on this problem. So the problem is a variant under isometries of M. That is nothing new. If the codomain is a surface, then it's also invariant under conformal changes of the metric here. Yeah? This is very similar to, when you're studying minimal surfaces, then you know that the problem of minimal surfaces invariant under isometries of the image manifold. You're mapping a surface into a Riemannian manifold, and it doesn't really matter. You can use isometries, but also, which is interesting, that it's invariant under conformal changes on the surface where you're coming from. So in many ways, the problem that I will discuss is sort of dual to the problem of mapping surfaces into Riemannian manifolds so they are minimal. Okay, it goes through all this theory that we are sort of in the dual situation. So what does that mean? So if you, as we all know, a surface can always be locally parametrized by isothermal coordinates on C. So that means if you're looking for local solutions to my problem, you can just assume that you're going into the complex plane, and that's exactly what I'm going to do. Okay.
There is a question in the chat. I will read you.
Please
Why do
read
you
it
need,
for me.
yes, why do you need dimension 2 on the manifold N?
That's a very good question. The thing is that if you have 3 or 4 or 5, then this result here is not true anymore. So what you need is, maybe I should go back. You see that this, what do you call it? Dilation. Yeah. This, if you take the gradient of this dilation, it will have a horizontal part and it will have a vertical part. Yeah? Do you understand? And in the higher dimensional case, then to get minimal, you need the gradient of this to be vertical. That means that the horizontal part has to be 0. That's a very, very special case. You can do it, but to me, not so interesting. Is that an answer to the question?
Yes. But
okay.
Here I have another question, because lambda was
Yeah.
assumed only continuous, and you are taking the gradient. Is only in the regular points, or?
No. If you look at this question here, everything here is differentiable. Everything here is differentiable. So if you divide, everything is differentiable.
Okay, thank you.
Yes. So, I mean, your question is a good question, but it follows from this equation here that it is C2, yeah? Okay. So, now, do we have solutions at all? So this is the solvable Lie group S3. And you see this is a very simple subgroup of SL3. So, for example, if you look at the metric, the Riemannian metric, it's quite simple. You only have things on the diagonal. But it turns out that there is no solution to the problem. And there is a very nice proof of this geometrical proof. So, as I told you before, if you're going into the complex plane, that means that the pre-emitters are minimal submanifolds. And if you have a minimal submanifold in a 3-dimensional Riemannian manifold, it has to be a geodesic. Yeah? So take a geodesic, call the tangent to the geodesic V, and then there is an orthogonal complement. And it turns out that if you take an element in the orthogonal complement, let's call it x, or x theta, because the orthogonal complement is two-dimensional, so you can turn that x around, Do you understand? So if you then, you have a element in the direction of the fiber, and then you have a whole choice of tangents in the orthogonal complement. And it turns out that if you have a solution, then the sectional curvature of V, which was tangent to the fiber, and any x orthogonal, it has to be constant. It's not so difficult to show. What does that mean? It's equivalent to the Ricci curvature only having two eigenvalues. But this Sol group has, the Ricci curvature has three different eigenvalues. So there is no solution. It's a beautiful geometric argument. Now, let's have a look at this. This is the three-dimensional Heisenberg. You see, the metric here is pretty simple, but here you see you have this symmetry in x and y. It turns out there is a solution, a global solution, but any solution to this problem is it has to be a restriction of these two. Nil has, the Ricci curvature has only two eigenvalues. Sol had three different. So it's a beautiful. Emilio, any questions?
No, the examples are pretty clear.
Yes, but it shows that, the geometry here is so interesting. And as far as I know, I have friends who are working in minimal surface theory, and they tell me that this lack of symmetry in this case also shows that it is very difficult. I talked to them maybe 5 years ago. They told that it's pretty impossible to produce with nice data minimal surfaces in this case. Is this something that is known to you?
No.
Or any honor? So there is also this duality between my problem and that of minimal surfaces. It's quite interesting. Now, Baird and Eels they started thinking about this after Fule and Okobi. They found this map here, which is the Hopf map, which we all know, from S3 to S4. It's globally defined. It's beautiful. So here,
Sorry.
Sorry?
I have a question, I think, about the previous slide. Can I read it in the chat again? From Lucas Larsen. Does having a local solution in any three manifold imply that Ricci has two eigenvalues at that point?
Yes. Can only have two.
Okay.
I mean, if you take the sphere or hyperbolic space, they only have one.
Okay, thank you.
But, Sol has three, and that kills the existence. I mean, the authors, when they proved there is nothing, they didn't see that at the beginning, but this is sort of geometric explanations that have come later, which I find beautiful. Okay, so Baird and Niels, they found that from S3 you have the Hopf vibration, which I guess we all know. Now Baird Wood, they found solutions. I just checked today. I thought they had not explicit formulas for them, but they actually have one. Something I, really looked at for 30 years. But they have one. And S4 less. So you have to think about it that S4 is compact, yeah? So you will never have a solution, harmonic solution from a compact manifold into the complex plane. That's the sort of, what is called? Maximum principle. But H3, yes. This guy here is not going into the complex plane, but S2, which is compact. Okay, so this is very special. Now, Baird, he found from H4, it is not very explicit, but, in both these cases, they have sort of a, how to say, they describe the solutions in terms of partial differential equations and so on, and prove that they do exist. But what I am interested in are explicit solutions, okay? So then I became a PhD student in Leeds, working with Wood, and I produced explicit examples, this case, and this case, and this case, and now I'm going to, in my talk about something, the duality. Those of you who know Riemannian symmetric spaces, they come in pairs, namely S3 and H3, they are sort of friends. And you see that I take this formula here, I only have to change it to this one, and then I have a solution on H3. And together with my clever first PhD student, we found a general method. If you have a solution to our problem, you can always find a solution on the dual, in the dual case. So this is maybe the simplest example. It's very easy, to find this. Now, after I was young and quite naive at that time, and after seeing this, I stated the following. So let M be an irreducible Riemannian space of dimension M greater equal to 2. For each point, there exists a non-constant complex-valued harmonic morphism defined on an open neighborhood U of F. If M is a non-compact type, then the domain U can be chosen to be the whole of M. When I stated this, I think in a talk in Leeds sometime, people laughed at me. You're a pretty crazy guy. That's okay. So what is a symmetric space? Emilio, do you think everybody in this symmetric seminar knows what a symmetric space is?
Yes, I guess pretty well.
Yes. Okay, it's a Riemannian manifold said to be a symmetric space if for each point P there exists a global geodesic reflective isometry, sigma, so that this is clear. So it means it takes a geodesic going through any point to the same geodesic, but running in the other direction. Yeah? I'll come back to this later. So this was my sort of crazy idea. Of course, I had no idea if it was true or not. Now, now we come to the method, our method of eigenfamilies. So we have a Riemannian manifold, complex plane, and then the Laplacian. In harmonic map theory, we often write it as tau for the tangent field, but this is just the Beltrami, Laplace Beltrami. And then, which fits to our problem is this. So you take you see that phi and psi are complex valued. That means that these gradients are also complex valued, yeah? So this here, G, this is the complexified, it's complex bilinear form, yeah, of the Riemannian metric on here. Any questions? So harmonicity and horizontal conformality, they're given by this, see? So we are looking for solutions where tau, the Laplacian, it's harmonic, but also horizontally conformal. That means that this is true. Now, then I was very lucky I got an email from a young lady, clever lady in Minsk in Belarus, and she wanted to become my PhD student at the time. As we all know, the political situation in Belarus is very difficult, but I invited her and I had to test her, and I had an extra copy of the book on this and sent it to her. And then she came here twice, and later because we didn't have money to hire her, she is now a lecturer at Uppsala in Sweden. Very nice lady. So in our work, we were able to, we defined this. So a set of complex valued functions is called an eigenfamily. Well, first of all, if phi is an eigenfunction to the Laplace operator and also to the kappa operator. So, I mean, this thing here has been studied for, I don't know, 200 years. But I guess this is new. I've never seen it anywhere else. But you see, because we are studying this and this is a very natural thing to sort of look at. So you might think that such elements do not exist, but here is a very natural example. If you take the orthogonal spheres and look at this, well, here it's clear on the orthogonals or any sphere, this is just constant, but I write it like this because it's useful for calculations, yeah? And then it turns out that they are eigenfunctions of the Laplacians. This is classical, but this is new, no? And useful for us. Then, if you look at the complex projective space and you pick alpha in between J and K as told here, then it turns out that these guys, also here, this is clearly, but for if you want to do calculations, I'm using a lot of, I'm using maple, and then, these sort of calculations are easy, very easy. And you see that you get here, this is well known, it's in a book by, what is it called, Jean Bourguignon, from the 70s, I guess, but this is new. Now, this was for me really a miracle. So let M be a Riemannian manifold. You have a finite eigenfamily. It means that all these elements are eigenfunctions of the Laplacian, and if you bring them together, they are eigenfunctions of the kappa operator of complex valued functions if P and Q are linearly independent homogeneous polynomials of the same degree, we have a lot of them, then this quotient is a non-constant harmonic morphism. I must say I tried this. I never believed it would work, but it works. And the proof is very simple. You could get sort of a good third-year student, maybe fourth-year student to prove this. But of course, this could be zero, and you don't want to operate there. So you have to be a bit careful. But this turned out to be a big surprise to us. Any questions? Caroline? No.
Sorry, that went down. Thank you.
Sorry. So the authors apply this machinery. So we did this, this was the very beginning. So we did this on these groups and also other groups. Now later, if you have an eigenfamily, both eigen to the Laplace operator and the kappa operator, then you can produce all these polynomials of a particular degree, and it turns out that they're also eigenfamilies. So this means you can, if you have an eigenfamily, you can produce infinitely many. And then it's very easy to show that the eigenvalues, they sort of follow this pattern here. Okay. Now, how do these eigenfamilies occur? You might have found this a bit strange, but I will now show you how it works in this simple case. So, equip the special orthogonal group, this guy, with the standard Riemannian metric induced by the Euclidean scalar product. This is the standard scalar product on this sort of Lie group. And this is the algebra. Now, if you do this, it's not too difficult. Then you see that this guy here is well known. This has been known, I don't know, for 100 years or something like this. But here, this is new. See the kappa operator, but the thing is that this disturbs us. If okay, so what you do, you take these are just the coefficients of SON. And then you have this disturbing factor here. So somehow you have to see too that this disappears. That's if you pick a isotropic element. What does that mean? Here, this is the bi-complex, inner product. If you pick this to be zero, that's easy. It then turns out that this is an eigenfamily. What does that mean? It means that these guys, they are eigen functions of the Laplacian, but also of the kappa. Now, this can be seen in many different ways, but if you have an isotropic element, like I'm talking about here in C4, that is well known, for example, from minimal surface theory in R4 or something, that they have to be of this kind, where these are two complex numbers. So for any, this is actually the how do you say, parameterization of Q2. You know, the the Q2. What is that? It's the subset of CP3. Is it called, what is it called? The quadric? I think the two-dimensional quadric in CP3. Yeah, this is how you do it, and this gives us the complex two-dimensional deformation. So here, for each P of this type, this is generated by two complex numbers. You get this whole family. But okay, this is just an example in higher dimensions. Any questions, Emilio? I want questions from.
Yes,
Yeah.
I have a question.
Yeah.
Maybe I'm wrong, but in your examples, the corresponding eigenvalue of your eigenfamilies is
Yes.
always the smallest positive eigenvalue in the spectrum. Is this true?
I don't know. But I don't know. Let's go here. You see that this is quite possible that you're talking about. But
I mean, in the examples, I know that the theorem works in general, but in the examples, I have the feeling that in the sphere, in the complex projective space, and now in SON, the eigenvalue is always the minimum. So my question is whether this is a general fact or maybe for every eigenvalue, this is true and you are showing the minimum because they are simple.
answer, but I think you're right, yeah, because the examples that I have, where did I show them? You know, this is possibly the easiest example you can think. You see here, this is just one, yeah. But the reason I write it like this is because I use Maple, and it is easiest for me to do the calculations using this formula. You understand? Because
Yes.
why? Because I can do the calculations here in R2N. So your question is very good, and I'm pretty sure that you're right, but I haven't really thought about it. Like here, you see, this thing here is just one, yeah? But if you want to use Maple or do calculations, it is important that they are fast, yeah? And that you do it as easy as possible. But I think, well, I have never, your question is very good. I've never thought about it, but I'm pretty sure that you're right, yeah? Now, I told you before that I had the conjecture about the Riemannian symmetric space in 1995. And then I had an absolutely fantastic PhD student. At that time, I was a lecturer. I was teaching, day in and day out. And I wanted to learn Helgeson's book on symmetric spaces. And it was very difficult for me because when I came home, I was tired teaching and so on. And then I had this fantastic student, Svensson, who is now head of department in Odense in Denmark. He's actually Swedish. And together we learned Helgeson's book. It took 2 or 3 years or something. And what we did, we solved the problem in, well, my conjecture, in all the cases except this bloody case here. We had no idea. I spent many nights, sleepless night on that. Not only me, but also my wife. And we couldn't solve it. But it says, let M be an irreducible Riemannian symmetric space other than this. This is non-compact, or is compact dual, which is compact, of course. Then for each P, there exists a non-constant complex valued harmonic morphism defined on an opus neighborhood about U of P. Yeah? If the space is non-compact, like the hyperbolic space or something, then the domain can be chosen for the whole of M. So we solved this in these years. You see, these are how many years? 14? Yeah, 14 years. With different methods, but later on we have seen it sort of more generally. But this caught the attention of my good friend, and I guess we all know Franz Burstel. He's a very clever guy. He solved the last part 2 years ago. He was here maybe 2 months ago and explaining how this did. So you can exclude these guys. Now the question is, does this hold for all homogeneous spaces? The homogeneous spaces have not been classified well. They have been sort of characterized, but I think a question, the answer to that question might not appear during my lifetime, but you never know. You never know. So this is a good good problem for the younger stars who are here. Now, our existing result for symmetric spaces has the following. Okay, so we were able to show this. We have no idea how to solve it in SP2, SU2. So, as most of you will know, the irreducible Riemannian symmetric spaces were classified by Elie Cartan. They constitute 20 countable infinite families and 24 exceptional single cases. They are quotients of V groups in dual pairs where UK is compact and this is non-compact. So here are the easiest cases we all know as N and hyperbolic space, the complex projective space, complex hyperbolic space, so on. So what we have found explicit complex valued eigenfunctions on all the classical irreducible Riemannian metric spaces. These are the sort of compact groups, the real, complex, and quaternionic Riemannians. You see that this is compact, this is non-compact, this is compact, this is non-compact. They come in pairs. Same down here. Okay, so from now on, we will focus on the rest. I will particularly explain this here, how the duality works. Quite interesting. So for the real special linear group and a non-zero element, we define the function by this. Okay, so this, you see that X is an element in this group and A is a non-zero element of Cn. Yeah? So this is well defined, and then you take the trace, and this is complex valued because A is complex valued. It then turns out it's very easy. We have done all this by, both by hand, but then to check, we have done it by computer algebra. That this is actually the eigenvalues. Now, you see that this part here tells you that this is SO invariant. So it actually induces a map on the quotient. But it's because this, the quotient from SL down to the quotient is a Riemannian subversion. It's easy to show that the same applies to the quotient and the eigenvalues are actually the same. Now, I will, you remember at the beginning, I told you about the Hopf map and then the dual Hopf map on the hyperbolic space. Yeah? This is something that goes over to this sort of Helgason theory that, and I will now explain it in this case. So, okay, you have this map here. Now, let us now extend the map on the complexification. Okay, so this is the complexification of this. Yeah? And it's exactly the same formula, except these real matrices are now complex. Huh? It then turns out that the restriction, so SUN is a subset, of course, a subgroup of this, of a subgroup, is also an eigenfunction, but with a negative eigenvalue. So you see that here you have these eigenvalues. You get the same eigenvalues here, but with a minus. This applies to all the Riemannian symmetric spaces. For example, if you take the sphere and the hyperbolic space, they are sort of dual friends. You always get this negative here. Now, this is, of course, SO invariant. You see, if this thing here, it's clear that this is SO invariant, and hence induces an eigenfunction on the quotient. Yeah? And the quotient map, the natural projection from SO or SUN down to this quotient is a Riemannian submersion. So the eigenvalues are the same, but of course, the quotient with the same eigenvalues negative. Yeah? So with this at hand, I did with Siffert, who is a professor in Münster, and Sobak, who was a master student of mine, and then I wanted him to stay in Lund, but we didn't have money, so he left for Siffert in Münster. Now he is a postdoc in Vienna. So we found eigenfunctions, just like I described in this example here, in all these cases. And remember, these cases are compact. So if you have solutions in the compact case, you can always find even global solutions in the non-compact. Remember that if you have a compact manifold like this, you will never find a global solution because of the what is it called, maximum principle. But in the non-compact case, it turns out that they are global. Now, studying all these cases, I had a brilliant master student. I gave him the job, or we studied it together, that all the examples we have, they actually come from the famous Cartan embedding. So, you know, there is a sort of general theory. You could use the Cartan embedding, which, what does it do? It takes a compact Riemannian metric space maps it into its isometry group, it's a Riemannian immersion. So all these examples that we found in the compact cases, they actually arise during this Cartan embedding. And now you can do the duality, which I have sort of tried to tell you a little bit about it without going into details. So all the examples that we know of in the compact case and then in the dual non-compact case, they all arise from this famous Cartan embedding. Was that a surprise? I don't really know. From the beginning, yes, but when we had studied this, I had that idea and had this clever master student who then went to Vienna. He's now a PhD student there, and together we found out that that was actually the case. So the theory is sort of, this should basically simplify the theory, you know. Emilio, what do you think of this?
Okay, we have very nice talk, and we have already 60 minutes of the talk. I was going to inform.
I don't know. Yes. Okay, I think I should stop. Yeah? Is that okay?
Yes. Well, actually, in the chat are asking that you continue. Yes, you can continue 5 minutes if you wish.
Okay. So this was the last. But it turns out that I have another clever student from Australia, Thomas Mann. I think there is a guy here from Australia who knows him. So if you have an eigenfunction, and then it turns out that if the fibre over 0 is a regular minimal, then it's a regular minimal manifold of codimension 2. So here, this is clearly a map from SL3. I talked about it before. And then this, if you put this equal to 0, you get a complete minimal submanifold of codimension 2. Here, this is the compact version. You see that I talked about earlier, this duality between the non-compact and compact. So this is a German lady, Eigenfamilies, and Larsen, well, Swedish-Danish guy. And here's a proof. What you do, you just have to prove that it's a subversion. I think I'll stop here.
Thank you very much. Very, very nice talk. Very entertainment.
I really enjoyed giving this talk. Yes.
Thank you very much. Okay, it's time for questions. Are there any questions?
Ines Scott, I'm expecting a question from you. Or Cesar. Cesar, what is your question? Cesar
No
is a
question.
long-standing.
It was very nice. It was very nice. No question. Not now. Next time I will ask questions.
Cesar is a long-standing friend of mine from Romania.
Hi, this is Michael Eastwood here. I do have a.
Sorry.
I have a question about much earlier in the talk. Much earlier in the talk, you were talking about examples on nil, and you said it was because the Ricci curvature had just 2 eigenvalues. So what about the Berger sphere? That would be another example.
Yes. Wait a minute. Berger sphere.
The Berger. So the Berger sphere.
Do you mean lens spaces or something?
Well, the Berger sphere is just another metric on.
Yeah, I understand you. Okay, so
Yeah. Okay.
you have the Hopf map, and then
Yes.
you sort of shorten the fibers. Is that right?
That's right.
You have solutions there, no problem.
Oh, you do. Oh, good. Okay. Thank you.
I don't know. This must have been discovered. I think it's in James Eales and Ratto wrote a book. Do you know that?
No, I don't know that one. No.
Okay,
So-
but I'm pretty sure it's in there.
Okay.
This was quite early on. We're talking about sort of 1992 or something. But of course,
Yes.
as I told you in the bibliography, in my bibliography, there are, I don't know, 400 references. It's impossible to remember everything.
Yeah.
Even though I have sort of edited it, people are surprising me all the time. It's 400, it's too much.
Okay,
then
we
we
have a
get-
question from Theodoros. Could you please ask
Yeah.
it?
Oh, yes, my friend from Greece. Yeah.
Yeah, very nice talk, Sigmundur. Very nice talk.
Thank you.
So, what I find really interesting is that you develop a method to produce even global minimal submanifolds in all these spaces, always of codimension 2. Yeah, right?
In the non-compact case, yes.
In the number case, right? So,
Yes.
my question is the following: can your method produce families, one parameter families, I don't know, of minimal submanifolds that are
Of course.
isometric?
Of course. Which are isometric.
Isometric, yeah.
Mhm. That's a very interesting question. Producing families is no problem, but if they are isometric,
Yeah.
very, very interesting. Of course,
Yeah.
harmonic maps and all this, is invariant under isometries of the domain, but I'm sure you're not talking about that. You're talking about
Yeah, exactly.
You're talking about submanifolds which are isometric but not concurrent.
Exactly. Yeah, that's my question.
Yes,
Yeah, of course. Yeah.
That's a very, very interesting question. We are meeting in Rostock in September.
Yeah, sure. Yeah, next
And
September.
then I will give you a good answer to that.
Yeah, that would be great. Yeah. And another question is, what about the topology of have you ever tried to understand the topology of these minimal submanifolds?
So the problem is that in the non-compact case, some of them are complete, yes.
Yeah.
But the topological questions are mainly interested in the compact case.
Sure.
But in that case, we have singularities and so on.
Oh.
This is a very, very interesting question. I think it's very difficult, actually.
Yeah.
But it would be interesting. My solutions are usually given by sort of quotients of polynomials, and what you would like to sort of read off these polynomials is, some topological, I don't know, Betty numbers or something like this. From I have no idea.
Yeah.
I have been asked these questions many times. I remember I was in Brussels maybe a year ago. I gave a talk about this, and
Yeah, it's tough. I presume
I don't know.
Okay. Thank you, Sigmundur. Thank you.
Okay.
Marco Sobak, I'm sure you have a question. Marco
Very nice
Soban.
talk. A very nice talk.
I would like to hear a question from you.
How was your day?
You are a former student of mine. You must ask a question.
Can you hear me?
Of course.
How much time did it take you to prepare this? I remember when I was a student, you always asked me how much time it took me to prepare the exercises.
You mean to prepare this talk?
Yes.
Maybe 3 days, something like that.
Very good, very good. So at least 3 sleepless nights.
Not for my wife. She has now her own room. I don't want to go into that. You know my wife, you have to be careful.
Of course.
She might eat me if I tell too much.
Okay, are there any other questions?
Theodoros, I look forward to meet you in Rostock.
Yeah, me too. Me too. Yeah.
Maybe we could have a beer together.
Sure, for sure. Not only one, maybe more.
Okay.
Emilio,
I propose to stop the recording and then we can chat without without being in YouTube in the future. Okay. So let's thank Sigmund again. Thank you very much. Very nice talk.
Thank you for listening.
Thank you for a really nice talk. I have